In this video, we will be solving first-order linear differential equations using integrating factor method. Integrating factor method is one of the widely used methods for solving first-order linear differential equations. Just a quick introduction to the steps we will be using in solving the first-order linear differential equations using the integrating factor method. The first step basically is to write the equation in this form, and ensuring that P of x and Q of x can be uniquely identified. We also see here that we have y prime, which is the first derivative of y, and that is why it is a first order in its form. If it is y prime prime, the second derivative, then it will no more be a first order linear differential equation, but a second order linear differential equation. So for the first order, you see the first derivative of y is what the form of this aspect looks like. So the second step is to find the integrating factor mu of x. The integrating factor mu of x is given by exponential raised to power the integral of p of x dx. So we talk more on this when we begin to solve problems. So now the next step would be then to multiply both sides of the equation by mu of x, which is the integrating factor. Now, taking the form of the equation as y prime plus p of x, y equals q of x, and multiplying the integrating factor with each of the elements will give us something like this. Now the next step will be to recognize the left-hand side as a derivative of the right-hand side. And that derivative, of course, it can be proven. Now, the derivative will be in form of the integrating factor multiplied by y. Now, the derivative of the integrating factor and y will usually give us everything on the left-hand side. So we also see more on that when we begin to solve problems. Now, the next step would be then to integrate both sides of the resulting equation from the previous step and then solve for y. All right, so let's solve the differential equation y prime minus 3y equals 5 exponential raised to power 2x. The first thing to do is to identify the fact that this is an ordinary differential equation, and of course a first order linear differential equation. Y prime here is the first derivative, and that shows we are dealing with a first order linear differential equation. So the general method of solving first order linear differential equation is to use the integrating factor method. In order to do that, the first step is to write the equation in standard form of y prime plus p of xy equals q of x. So now when we look at the standard form of solving the first order linear differential equation using integrating factor method, the standard form is y prime plus p of x, y equals q of x. Now relating this with the problem, from the problem we see that the coefficients of y prime is 1, and it is similar, it is 1 here, that's okay. Now, we relating the equation with the standard form will then show that the coefficients of y from the question is minus 3. So that shows that p of x will equal minus 3. and q of x will equal 5 exponential raised to power 2x. So the next step will now be to find the integrating factor. Of course, from the previous step, we have been able to identify p of x and q of x. Now the integrating factor, which is represented by mu of x, is given by this equation. So this, just have to know, this is the equation of the integrating factor. Already we know p of x. So what we just do then is to substitute minus 3 for p of x and integrate in this equation as appropriate. So now that gives us exponential raised to power the integral of minus 3 dx. Now when we integrate this, we have exponential raised to power minus 3x. Now this is the integrating factor. The next step is to multiply the entire equation given the problem by the integrating factor. The integrating factor, of course, is this. So we multiply all through the equation. We multiply the equation through by the integrating factor, which is exponential raised to power minus 3x. So now when we multiply this by the integrating factor, we get this trade-off equation if done appropriately. So the next thing is to simplify the left-hand side as a derivative of the integrating factor and y. Now, using product rule, of course, recall that this is the integrating factor multiplied by y. Okay then. Now, using the product rule, differentiating this entity will, of course, produce the whole left-hand side. So this is right. This is correct. So you can test that to ensure, just to prove that this derivative of the product of the integrating factor and y will give the entire left-hand side of this equation. So moving on from this step, we then integrate both sides with respect to x. So when we integrate this side, we'll be left with exponential raised to power minus 3x y, that's multiplied by y, equal the integral of the right-hand side, which is this. Now the integral of the right-hand side will give us minus 5 times exponential raised to power minus x plus c, if done appropriately. You know, just to further explain that, now this will equal 5 is a constant, so you bring it out, then you integrate the exponential minus x, the x. Now to integrate exponential raised to power minus x, the minus sign will come, we just bring down the minus sign, that will give us minus 5, and the integral of e raised to power minus x is still the same thing as e raised to power minus x. So then you bring down, then you write out your constant of integration, which is plus c. Of course, that is just the normal integration rules you should be conversant with. And all right then. So the integral of this gives us what we've got here. So the next thing now to solve for y will be to divide both sides by exponential raised to power minus 3x. Now, dividing this by exponential raised to power minus 3x will give us minus 5 exponential raised to power 2x. You know, what that will result to will be minus 5 all over exponential raised to power minus 3x and exponential raised to power minus x here. And you know, according to the law of indices, these are of the same base, so it will then transform to minus 5 exponential minus x. Then because they are of the same base, we can then have, because of the division here, that will be subtracting the power with, because they are of the same base. So when you subtract minus 3x this way, so minus times minus will give us plus, so we then be left with minus x plus 3x, and that will give us 2x, and that is how we got this. Now when we divide this constants, when we say the constants all over exponential raised to power, so I will divide this constants by exponential raised to power minus 3x. So we can also bring the exponential raised to power minus 3x up, and by doing that, you see the negative sign here would disappear. Okay, let me just explain that as well. If we have c raised to power exponential minus 3x, so we can assume that this equals constant exponential raised to power 0. No, anything raised to power 0 is 1. So, and because it is the same base as this, so according to law of indices, we can have minus 3x. So you then subtract the power. So when we subtract the power, minus times minus becomes plus, and exponential, what we'll be left with will be constant multiplied by exponential raised to power 3x. So that is how we got here. So we have c exponential raised to power 3x, because 0 plus 3x will simply give us 3x. All right, let me just wipe this off. Okay. All right then. Yes. So, and here we go. So that gives us the solution to the differential equation here. The solution becomes y equals minus 5 exponential raised to power 2x plus the constant multiplied by exponential raised to power 3x, and that is the final answer. Now from here, from step 3 to step 4, alternatively, is instead of taking that route, you can as well, from the second step here, just move on to solve for y. And y as a basic rule, y of x, which is the solution to the differential equation, equals 1 all over the integrating factor, then open brackets, integral of the integrating factor the product of the integrating factor and q of x, the x plus constant. So we integrate this, multiply with this, and that will give us the solution. So let us try that out. The integrating factor as determined from the second step is exponential raised to power minus 3x. So let's substitute that for the integrating factor here. That will be 1 all over exponential raised to power minus 3x. So multiplied by the integral of the integrating factor, which is still the same thing as this, then multiplied by the q of x. Q of x as determined or as identified earlier is 5 exponential raised to power 2x. And that is also what we've got here. So then what we then want to do is bring out this constant, which is 5, and integrate what we've got left. Now, according to law of indices, because this and this are of the same base and they are being multiplied, we can just simply add the power. So that gives us minus 3 plus 2x, and that gives us minus x. So then this is what we are left with to integrate now. So then when we integrate this, we get minus exponential raised to power minus x, and when we multiply that with 5, we have minus 5 exponential raised to power minus x plus c. This c will still come up in the integral. Now when we then multiply what we've got here with this aspect of this side, we then have minus 5. Of course, we use the law of indices also, where we subtract the power. That's, you have exponential raised to power minus x minus, in brackets, minus 3x, and that will give us plus. So we have minus x plus 3x, and that will give us 2x. So that is how we got this. And of course, when you multiply this side with this minus 3x, just as earlier done, we got it off the other time. So as earlier done, we also have c multiplied by exponential raised to power 3x. You can see that the solution is, the final answer is the same. So you can either follow through from the third step to solving to the final answer, or from this second step you can just decide to use these routes. You will also get the answer correctly. All right, let's look at another example. Solve the differential equation x raised to power 2 y prime plus xy equals 4x raised to power 3. Now, we need to know that this problem is a first order linear differential equation. So, and as such, we start off the solution by rearranging the equation so as to have it in the form of the general standard form for solving first order linear differential equations, which is y prime plus p of x y equals q of x. So in order to do that, we divide through by x squared so that the coefficients of y prime can be 1. So now when we do that, we divide this by all through by x raised to power 2, we get, this is what we get. Now here we can relate this resulting equation with the standard form. And in doing that, we can identify P of x. So P of x is 1 all over x, and Q of x is 4x. Now, following the identification of P of x and Q of x, we can then move on to the next step, which is to find the integrating factor mu of x. The integrating factor mu of x generally equals exponential raised to power P of x integral of P of x dx. Now, substituting 1 all over x for P of x and integrating as appropriate gives us exponential natural log of x. Now, there is a property of logarithms that states that when you have exponential raised to power natural log of a function f of x, then what you have as your answer is simply f of x, whatever f of x is. In this case, let's say f of x equals x. So you should be conversant with that property of logarithms, really. So now basically this equals x. So then we move on to the third step, which is to solve for y. And the general solution for the first order linear differential equation is in this form. You just have to know this. It is a straightforward approach than following it stepwisely as we did in the previous example. So now y of x equals 1 all over mu of x, which is the integrating factor, which we have earlier determined here to be x. Now open brackets, integral of the integrating factor, which is mu of x, multiplied by q of x dx plus constants. Now q of x is 4x, and mu of x, which is the integrating factor, is mu of x is x, which is this now. Now 1 all over mu of x, which is 1 all over x. So now what we then do is multiply this out and bring out the constant term, which is 4, and that we've done here. So we now have x raised to power 2. So now when we integrate x raised to power 2, it gives us x raised to power 3 all over 3, of course, plus the constant term. Now 4 multiplied by 1 gives us 4 all over x. Now when we just multiply this out, 4 multiplied by x raised to power 3, then all over 3 multiplied by x, which is 3x. So x cancels one of the x here, and we are then left with this final answer, 4x raised to power 2 all over 3 plus c all over x, as we also multiply 4 all over we also multiply 1 all over x with the constant term here. So this is the final answer. Okay, here we want to look at just one more example. Solve the differential equation x plus 1 in brackets y prime plus 2y equals x raised to power 2. Now this is a first order linear differential equation. We must indeed, of course, identify that. Knowing the type of equation is will give insight into knowing the approach to solving it. So because it is a first order linear differential equation, we follow the steps to solving first order linear differential equation. And the standard form of first order linear differential equation is this. That is y prime plus p of x, y equals q of x. So now, in order to get this problem into this form, the coefficients of y prime must be 1. So what we then do is to divide through by x plus 1. So when we divide this through by x plus 1, we have this expression here. And with that, we can now compare this expression with the standard form, so we can identify p of x and q of x. So p of x equals 2 all over x plus 1, and q of x equals x raised to power 2 all over x plus 1. Now with this, we can move on to the next step. The next step is to find the integrating factor. So the integrating factor mu of x is given by this expression, exponential of raised to power integral of p of x dx. Now p of x is 2 all over x plus 1. Therefore, substituting 2 all over x plus 1 for p of x gives us this, and well, we can integrate that. Integrating this gives us exponential raised to power 2 natural log of x plus 1. Now these two can come up here and become x plus 1 raised to power 2. And as a property of logarithms, there's a property of logarithms that states that when you have exponential raised to power natural log of a function, that function becomes the answer. In other words, the exponential and the natural log cancels out to give you the function as the answer. So now this is what we've done. We just invoked the property of logarithms that relates to this to get this. All right, simply done. The next step now is to find to solve for y directly. So now this is the standard solution for y when solving for first order linear differential equations. So what we just do is to plug in the various values for the integrating factor mu of x and q of x. Now the integrating factor mu of x is x plus 1 raised to power 2. So we're substituting that here, gives us this. Now x plus 1 raised to power 2 times q of x is x raised to power 2 all over x plus 1. So this we've also written down here. So x plus 1 cancels one of the x plus 1 here, and what we are left with is x plus 1 times x raised to power 2. So x raised to power 2 times x gives us x raised to power 3, plus 1 times x raised to power 2 gives us x raised to power 2 dx plus c. So integrating x raised to power 3 and x raised to power 2 simply gives us x raised to power 4 all over 4 plus x raised to power 3 all over 3. So multiplying that, of course, plus c. Now when we multiply those two guys with this, it will simply give us x raised to power 4 all over 4 multiplied by x plus 1 raised to power 2 plus x raised to power 3 plus, all over 3, open bracket, x plus 1 close bracket squared, plus we also multiply this and the constants. So that gives us constant all over x plus 1 in bracket raised to power 2, and that is our final answer. All right, you can just pause this video and try to work on these exercises. And if attempted correctly, these are the solutions, the answers expected from these exercises.